this video is only an introduction. It's only like a brain teaser of some of the initial problems that we're going to encounter as we begin our study. So it is not my intention to right away develop the entire theory behind a tangent line and the slope of that line. That's the role of chapter 3. Before we even get to that, we have to go through all of chapter 2 and learn about limits. So there's a lot going on here before we can get to settle the issue of a tangent line. But what I want to do is to give you an idea of how the discussion of chapter 3 is going to begin, how we are going to start investigating what a true definition of a tangent line is, and therefore what is really the slope of a tangent line. How do we really find the slope of a line that is tangent to a graph at one point? So that's the goal here in this intro, just to give you an idea behind that theory. So we don't know right now what a tangent line is. All that we know is, or all that we have is a description of what it should look like. A tangent line somehow should be a line that hopefully it intersects the graph at just one point. But again, this is a little bit fishy definition. What we do know, however, is what a secant line is. Secant. The discussion of a secant line is something that arises in a grade 8 or a grade 9 math class. Typically, that's when it pops. What is a secant line? A secant line is a line that intersects a curve at least 2 different points. So the intersection consists of 2 points or more. For example, let's say that I draw a curve, something like this. Okay, so this is my graph. And let's say that I draw a line like this. This line immediately becomes a secant line because I have points of intersection. I have 3 points of intersection, right? To be a secant line, you have to have 2 or more points of intersection. Here I have 3 points of intersection, so this line becomes a secant line. And because a secant line requires at least 2 points of intersection, I can actually calculate the slope of that line, right? If I have 2 or more points, I have enough points to be able to calculate the slope of that line. So, knowing that and having that in my toolbox, I'm going to go ahead and take advantage of that. We're going to pick a point Q, let's call it Q, and it's completely random. We're going to pick a point on that parabola, on that graph. And we are going to draw the secant line that is going to pass through point P and point Q. So in order to do that, let me connect. I'm going to connect point P and Q right here. So what I have done is I have created, or I have drawn, the secant line that is passing through points P and Q. What is really nice about that is that because I have 2 points, I have point Q and point P, 2 points on that line, I can easily find the slope of that line. So I know, let's call this slope over here, the slope of line PQ. And we know that we can use the formula y2 minus y1 over x2 minus x1 to calculate the slope of that line. But then, could the slope of line PQ be a good approximation for the slope of the tangent line? I mean, think about it. Q is still very far away from P. So the slope that we get of this line will still be very far off from the slope of the possible tangent line. remember that we are still hoping. Let me try to draw a tangent line, or what we believe is a tangent line. Let me always clarify that, even though I'm saying a tangent line. A tangent line, based on what the descriptive definition that we have, a tangent line should look like the red one that I just drew right here. Should only intersect point P. It should only intersect the graph at point P, and then it should move away from that graph. So hopefully we can still keep a bit of that definition in place. So this should be really the slope of the tangent line. This should be the true slope of my line right here, little m. But right now, the best that I can do is to calculate the slope of the secant line, but I know that Q is too far away from P. So the slope of PQ is not going to be close enough to the slope of what appears to be the tangent line, the red line. So then, a solution, or a possible solution for that, is to choose another point. Let's pick a point, let's say, a little bit closer to P. Let's call this point Q prime. And we're going to go ahead and we are going to again connect points P and Q prime with another secant line. Okay, so this is going to be the green line right here. And we're going to use the same slope formula to calculate the slope of my new secant line, the green line. We're going to use y2 minus y1 over x2 minus x1. Now, the slope of this green line, it's definitely going to be a little bit closer to the slope of the red line, the tangent line, because Q prime, it's a little bit closer to P than point Q. So then we go, okay, this is good. Maybe we're getting something, but this is not good enough. We need to be closer to P. So why don't we then pick a point that is actually closer to P? I'm going to be using yellow here. And let's connect again. Let's create a secant line that is going to pass through the yellow point. Let's call the yellow point Q double prime. Let's connect Q double prime and point P. So the yellow secant line. And let's calculate another slope. So again, this is going to be the slope of line PQ double prime using the same formula as above right here. And we go, okay, because Q double prime is closer to P, we should expect that the slope of PQ double prime, the slope of the yellow secant line, is going to be closer to the slope of the red tangent line. So I'm hoping that you're starting to get the idea of what we're doing here. What we are doing is we are moving the point Q that we started with. We have been moving that point closer and closer and closer to P. We have been drawing secant lines. A secant line has at least 2 points of intersection with the graph. We calculate the slope of that secant graph, and then we're going to start collecting those slopes. Let's do one more point. Let's say now that we get even closer to P. I'm going to do this in pink. I'm going to pick a third point right there. We're going to call this point Q triple prime. We're going to go ahead and connect point P and Q triple prime. Let me try to get my ruler here aligned. And when I do that, again, try to follow the pink line that I'm drawing right here. We're going to create another secant line. But the nice thing about this secant line is that the slope of this secant line should now be closer to the slope of the red possible tangent line. So what we have done is the following. We came and we chose a point on the graph Q, we drew the secant line, and we calculated the slope of that line. But because Q was pretty far away from P, we knew that the slope of that line was not going to be too close to the slope of the tangent line. But nonetheless, that was a start. Again, we calculated the slope of line PQ, but that's not good enough. So we came and we picked another point on that line, on that graph, Q prime. Now Q prime was a little bit closer to P. So when we calculate the slope, we know that the slope of line PQ prime is going to be a little bit closer to the slope of the red tangent line, but still not good enough. So we came and we picked another point on the graph and we calculated the slope of PQ double prime. That slope definitely getting a little bit closer to the slope of the red tangent line, but again, we want more precision. So we came and we picked a third point on that graph, Q triple prime, and we calculated the slope of line PQ triple prime. And then if you continue getting points and calculating slopes that are closer, every time you are closing the gap, and the gap becomes smaller and smaller and smaller. So then what you are hoping to achieve is to somehow get a decent approximation of the slope of the tangent line by considering the limit of the slopes of the secant lines. And hopefully the limit of those slopes are going to quickly converge. They will start approaching the true slope of the tangent line. So see, what we did here was we came and we chose a random point Q on the graph and we calculated the slope. But again, this point was too far from P. So then we came and we started choosing points Q prime, Q double prime that were moving closer and closer and closer to P. And we calculated the slopes of those secant lines. And here what we're trying to do is to now look at all those slopes, look at the values of the slopes that we have collected. And we want to be able to see that now these values are converging to something fixed. Hopefully the true value of the tangent line, of the slope of the tangent line.